Chapter 6, the muscular system. As you can see, we have several learning objectives for this chapter to include describe similarities and differences in the structure and function of the three types of muscle tissue, define muscular system, define and explain the role of the following: endomysium, paramysium, epimysium, tendon, and aponeurosis, describe the microscopic structure of skeletal muscle, and explain the role of actin and myosin-containing myofilaments. Describe how an action potential is initiated in a muscle cell. Define graded response, tetanus, isotonic and isometric contractions, and muscle tone as these terms apply to a skeletal muscle. Define origin, insertion, prime mover, antagonist, synergist, and fixator as they relate to muscles. Demonstrate or identify the different types of body movements. List 7 criteria used in naming muscles. Name and locate the major muscles in the human body and state the action of each. Explain the importance of a nerve supply and exercise in keeping muscles healthy, and describe the changes that occur in aging muscles. There are 3 types of muscles: skeletal, smooth, and cardiac. I'll give you a brief overview of the 3 different kinds, but the primary focus of this chapter is skeletal muscle. So they differ in cell structure, body location, and how they are stimulated to contract, but they are similar in some ways. So the cells of skeletal and smooth muscles are elongated. They're called muscle fibers. And myofilaments enable muscles to contract or shorten. Whenever you see prefixes like these, myo, mis, or sarco, you'll know that muscle is being referred to in some way. And for example, in muscle cells, the cytoplasm is called the sarcoplasm. So that's how you know it's talking about muscles. So here in the diagram on the right, you can see the different body locations. So skeletal muscle is attached to bones, or for some facial muscles, it's attached to the skin itself, while cardiac muscle is only found in the walls of the heart, and smooth muscle is in the walls of hollow organs other than the heart. So we'll talk more about cardiac and smooth muscles as we move further down in the class. Cell shape and appearance. So skeletal muscle is single, very long, cylindrical, multinucleate, so it has multiple nuclei within the cells with obvious striation, so it looks striped. Cardiac muscle is branching chains of cells, uninucleate, so single nucleus, striations, again, those stripes, intercalated discs. And then smooth muscle, single, fusiform, one nucleus, no striation, so it does not have the same stripes that are characteristic in your skeletal and your cardiac muscle. Connective tissue components. So in a skeletal muscle, we'll learn more about this as well. You have the epimysium, paramysium, and endomysium. In the cardiac muscle rather, endomysium is attached to the fibrous skeleton of the heart, and then in smooth muscle, you have the endomysium. Regulation of contractions. So skeletal muscle is voluntary. There are some movements that skeletal muscle will make based on the nervous system, so things like your reflexes, but for the most part, it's voluntary. Cardiac and smooth muscle are both involuntary. So as I've said before, we want that those cells of the heart to be involuntary. We don't want to have to think, oh, my heart needs to beat. We don't want to think, oh, my stomach and my intestines need to digest. You know, we want those things to be involuntary. So the heart has an internal pacemaker, which again we'll learn more about in our cardiac chapter, but it also has nervous system controls and hormones that affect it. Smooth muscle is involuntary. Nervous system controls hormones, chemicals, and stretch determines the movement or the utilization of those muscle cells. Speed of contraction. So for skeletal muscles, we have slow to fast, which again, we'll talk more about that later on in this chapter. And then cardiac muscles, we have slow, smooth muscles, very slow. Rhythmic contraction. So skeletal muscle does not have rhythmic contraction, while heart muscle and in some of smooth muscle, there is that rhythmic contraction, like, you know, your heart is beating at hopefully a regular rate, so it is rhythmic. So let's establish that first. In general, when somebody says muscular system, they're referring to skeletal muscle. So that, again, is our focus for this chapter. So skeletal muscle fibers, they're the largest of the muscle fibers. They're cigar shaped, that cylindrical shape with multiple nuclei. They attach to the skeleton, or like I said, in some cases, the skin itself. They help to form the smooth contours of the body. It's striated muscle. It's known as striated muscle. You know, it appears to have stripes. It is, again, a voluntary muscle, which can be activated by reflex. It can contract rapidly with great force, but must rest after times of activity. So you can see here in the diagram that each muscle fiber is enclosed in a delicate connective tissue sheath called the endomysium. So you can see the endomysium in the center around each muscle fiber. And then several sheath muscle fibers are then wrapped by a coarser fibrous membrane called the perimysium. So it's grouped muscle fibers, and the perimysium surrounds that. And this forms a bundle of fibers called a fascicle. Many fascicles are bound together by even tougher overcoat of connective tissue called an epimysium, which covers the entire muscle. So the ends of the epimysium that extend beyond the muscle, if you think about a piece of candy and the wrapper around it, like a mint or something, they blend either into a strong tendon or a sheet-like aponeurosis. So the aponeurosis will indirectly attach to the muscle to bone, cartilage, or another connective tissue. So tendons have some other functions. So they anchor muscles and they provide durability and conserve space. They're mostly made of tough collagen fibers, so they can cross rough bony projections without tearing. Muscle would tear itself, so the tendon is important. Because they're relatively small in size, more tendons than fleshy muscles can pass over a joint. So an easy way to think about this is that the muscles have a large belly, so that center part is larger and it tapers down to a tendon at the end. However, muscles can vary considerably in the way their fibers are arranged. Many are spindle shaped, as we just described here, but in some others, the fibers can be arranged in a fan shape or a circle or a feather-like pattern, which we'll look at further on in the lecture. Here's just a brief overview of smooth muscle and cardiac muscle. Again, this will not be our focus here in this lecture about the muscular system, but smooth muscle, it's your visceral muscle. It's non-striated and involuntary. So we consider this the marathoner when you're comparing it to skeletal muscle, which, like I said, can do profound work but needs to rest. It's the sprinter, and your smooth muscle is the marathoner. It's doing work constantly and generally at the same pace, and can maintain that work for a long time. So the cells don't tire out very easily. It's found mainly in the walls of the hollow tube-like organs such as your stomach, urinary bladder, and respiratory passages. Cardiac muscle, it's found only in the heart. It forms the bulk of the heart walls, striated, uninucleate, and involuntary. And you can see here in the image in B, the way it's wrapped around, they're arranged in a spiral or a figure 8 shaped bundle. And this just allows the heart, when it contracts, for its internal chambers to become smaller, forcing blood on a one-way path. Ideally, deoxygenated blood into one side and oxygenated blood out the other side, which again, we'll focus on that more in the cardiac chapter. So let's talk about some of the muscle function. So obviously, production of movement is very important. Your skeletal muscles are responsible for your body's mobility, including all locomotion, so walking, swimming, if you're a cross-country skier, etc. And it allows you to manipulate things with your limbs, which is important just for your everyday tasks, whether that's gross motor movement, fine motor skills, They enable us to have quick responses to our outside environment. So you're crossing the street, a car is coming, you jump out of the way. That's partially your skeletal muscle. Obviously, there's some neurological functions and things happening in your body, but your skeletal muscles are the action. And it allows you to express your emotions. For some of us, lack of emotion. For some of us, RBF, whatever. That's all skeletal muscle. Additionally, it allows you to maintain posture and body position. So this is how your skeletal muscles are responsible for keeping you erect when you're standing, when you're sitting. Even if you're slouching, your skeletal muscles are still responsible for helping you fight gravity. It stabilizes joints. So muscles and tendons reinforce and stabilize joints. So that's why if you have ever been to physical therapy with a knee injury, part of that rehabilitation is strengthening, the muscles in your thigh to support the knee. It's not just the joint itself. They generate heat. So it generates body heat as a byproduct of contraction. As the ATP is used to power muscle contraction, 3/4 of it is lost as heat. So skeletal muscles make up about 40% of body mass, and it's the muscle type most responsible for generating heat. And additional functions include smooth muscle that forms valves that regulate the passage of substances, dilate and constrict our pupils, and make up the erector pili muscle. So we talked about this in the lecture about skin when we were talking about hair. Skeletal muscles form valves that are under voluntary control and enclose and protect fragile internal organs. So let's talk more about the microscopic anatomy of the skeletal muscle. So as I mentioned before, skeletal muscle is multinucleate, which you can see in this microscopic photo at the bottom right of the slide. Oval nuclei beneath the plasma membrane, that's where they aggregate, they congregate, and the plasma membrane in a muscle cell is called the sarcolemma. So remember, sarco is that muscle prefix. The nuclei are pushed aside by ribbon-like organelles called myofibrils, myo meaning muscle, alternating I light bands and dark A bands along the length of the myofibrils give the muscle fiber its striated, striped appearance. And the I band has a midline interruption called the Z disc, and the A band has a lighter central zone called the H zone. In the middle of that H zone is the M line that contains tiny protein rods that hold adjacent thick filaments together. So there are two types of thread-like protein myofilaments within each sarcomere, and the thick filaments are made mostly of bundled molecules of the protein myosin. Notice that the thick filaments extend the entire length of the dark A band. You can also notice that the mid parts of the thick filaments are smooth, but then their ends are studded with small projections, which you can see at the bottom of the left image in C. These projections, or myosin heads, contain ATPase enzyme activity and split ATP to release the energy used for muscle contraction. The myosin heads also form cross bridges when they bind to the thin myofilaments during contraction. So myosin filaments are attached to the Z disc by titin, T-I-T-I-N, elastic filaments that run through the core of the thick filaments. The thin filaments are composed of the contractile protein, actin, plus some regulatory proteins that play a role in allowing or preventing the building of myosin heads to actin. The thin filaments are anchored to the Z disc. Notice that the light I band includes parts of two adjacent sarcomeres and contain only thin filaments. Although they overlap with the ends of the thick filaments, the thin filaments do not extend into the middle of the relaxed sarcomere. That's the central reason the H zone looks lighter. When the actin-containing thin filaments slide towards each other during contraction, the H zones disappear because the actin and myosin filaments completely overlap. Another organelle to take note of is called the sarcoplasmic reticulum, SR. If you recall from our lecture on cells, it's kind of like the endoplasmic reticulum, and it's the specialized smooth endoplasmic reticulum that is responsible for the storage of calcium and its release on demand when the muscle fiber is stimulated to contract. So this image is just showing us how the nerve stimulates that muscle movement. So to contract, skeletal muscle fibers must be stimulated by nerve impulses. One motor neuron may stimulate a few muscle fibers or 100 of them or hundreds of them. A single motor unit consists of the one neuron and all of the skeletal muscle fibers it stimulates. When the axon, which is the long thread-like part of the neuron, reaches the muscle, it branches into the axon terminal, each of which forms junctions with the sarcolemma of the different muscle fiber. These are called neuromuscular junctions. These neuromuscular junctions contain synaptic vesicles filled with a chemical referred to as a neurotransmitter. The neurotransmitter then stimulates the skeletal muscle, and it's called ACH or acetylcholine, and that's what the neurotransmitter that's responsible for stimulating skeletal muscle. While they are close, the nerve endings and the muscle fiber membranes never touch, and the space between them is known as the synaptic cleft. Now that we've established what the neuromuscular junction is, let's talk about what happens there. So 1, the nerve impulse reaches the axon terminals. 2, calcium channels open and calcium enters the terminal. 3, calcium entry causes some of the synaptic vesicles in the axon terminal to fuse with the cell membrane and release acetylcholine. 4, this acetylcholine diffuses across the synaptic cleft and attaches to membrane receptors in highly folded regions of the sarcolemma. 5, if enough of this acetylcholine is released, the sarcolemma at that point becomes temporarily even more permeable to sodium ions, which rush into the muscle fiber, and to potassium ions, which diffuse out of the muscle fiber. More sodium ions enter than potassium leaves, and this imbalance gives the cell interior an excess of positive ions, which reverses the resting electrical conditions of the sarcolemma, this is called depolarization. It ends up opening more channels to only allow sodium ions to enter. This movement of ions generates an electrical current called an action potential. Once begun, the action potential is unstoppable. It travels over the entire surface of the sarcolemma, conducting the electrical impulse from one end of the cell to the other, and the result is the contraction of that muscle fiber. And then 6, while the action potential is occurring, the enzyme acetylcholinesterase, ACHE, present on the sarcolemma and in the synaptic cleft breaks down acetylcholine to acetic acid and choline to prevent continued contraction of the muscle fiber in the absence of additional nerve impulses. So at that time, that's when your muscles relax. If we didn't have this last step, that ACHE, that enzyme to break down acetylcholine, you would just be in a continual muscle contraction, which is not very functional. So the series of events we just described on the last slide can be likened to a flame consuming a dry twig. So in A, the first event is igniting of a dry twig. It's holding the match flame under one area of the twig. And the second event is the twig bursting into flames when it has been heated enough and spreading the flame to burn the entire twig. B, you see the first event is exciting a muscle fiber and rapid diffusion of sodium ions into the cell when the permeability of the sarcolemma changes. The second event is the spreading of the action potential along the sarcolemma when enough sodium ions have entered to upset the electrical conditions of the cell. Now let's talk about the sliding filament theory. So we just talked about the events that happen at the neuromuscular junction that lead to an action potential. Now we'll describe excitation, contraction coupling, which is the combining of what just happened with what's about to happen, and the cross-bridge cycle during which myofilaments overlap to a greater degree in sarcomeres and the whole muscle shorten. So the sliding filament theory kind of addresses the question of what causes the filaments to slide. The formation of cross bridges when the myosin heads are attached to the actin requires calcium ions and ATP, and the ATP obviously to provide energy, and it provides it to the myosin heads. But where does the calcium come from? Action potentials pass deep into the muscle fibers along membranous tubules that fold inward from the sarcolemma and inside the cell in a process called excitation, contraction, coupling. The action potential stimulates the sarcoplasmic reticulum to release calcium ions into the cytoplasm. The calcium ions trigger the binding of myosin to actin, initiating filament sliding. When the action potential ends, calcium ions are immediately returned to the sarcoplasmic reticulum storage areas. Regulatory proteins return to their resting shape and block myosin binding sites, and the muscle fibers relaxes and settles back to its original length. This whole series of events takes a few thousandths of a second. So let's look more at this image on this slide. In a relaxed muscle fiber, the regulatory proteins forming part of the actin myofilaments block and prevent myosin binding. When an action potential, AP for short, sweeps along the sarcolemma and a muscle fiber is excited, calcium ions are released from intracellular storage area, aka the sacs of the sarcoplasmic reticulum. The flood of calcium acts as a final trigger for contraction. Because as calcium binds to regulatory proteins on the actin filaments, the proteins undergo a change in both their shape and their position on the thin filaments. This action exposes myosin binding sites on the actin to which myosin heads can attach, and the myosin heads immediately begin to seek out those binding sites. The binding of myosin to actin constitutes cross-bridge formation. So using ATP, free myosin heads are cocked, much like an oar ready to be pulled on for rowing, and myosin attachment to actin causes the myosin heads to snap or pivot towards the center of the sarcomere in a rowing motion. When this happens, the thin filaments are pulled slightly towards the center of the sarcomere, and ATP provides the energy needed to release and recock each myosin head so that it is ready to attach to a binding site farther along the filament. There are a lot of good videos in your ebook showing, I think there's 3 in here, showing how action potential causes calcium ion release, the role of calcium in the excitation, contraction, coupling, and sliding filament mechanism of contraction. So I encourage you to go watch those. So graded responses. Graded responses or graded muscle contractions can be produced in 2 ways. The first way is by changing the frequency of muscle stimulation, and the second is by changing the number of muscle fibers being stimulated at one time. So let's first talk about muscle response to increasingly rapid stimulation. So although muscle twitches, which are single, brief, jerky contractions, sometimes result from certain nervous system problems, this is not the way our muscles normally operate. In most types of muscle activity, nerve impulses are delivered to a muscle at a very rapid rate, so rapid that the muscle doesn't get a chance to relax completely between that stimuli. And as a result, the effects of the successive contractions are then summed together. The contractions of the muscle get stronger and smoother. This is when we see that the muscle is exhibiting unfused tetanus or incomplete tetanus. When the muscle is stimulated so rapidly that there's zero evidence of relaxation seen, the contractions are completely smooth and sustained, the muscle is infused tetanus or complete tetanus. So we can see here in the image on the right, a single stimulus causes a muscle contraction or twitch. The muscle doesn't have time to completely relax and be, and this is when we start summing those contractions. You can see multiple twitches and no relaxation, and you can see that the last 3 hills in C are all equivalent, but this is still considered unfused tetanus because there is some relaxation, just not complete relaxation between the twitches. And then fused tetanus is when you have this nice smooth line at the top. There is no relaxation happening. It is maintaining the same frequency or strength of contraction. And then muscle response to stronger stimuli. So tetanus produces stronger or more forceful muscle contractions, but its primary role is to produce smooth, prolonged muscle contractions. So the force of a muscle contraction correlates with the number of cells stimulated. So when only a few fibers are stimulated, the muscle as a whole only contracts slightly. And when motor units are all active and all muscle fibers are stimulated, the muscle contraction is as strong as it can get. So this is why we can do slight to vigorous work. That's why the same hand that can lift a heavy weight or heavy books can also just lift a single sheet of paper. So this has to do with how many fibers are being stimulated. Now let's talk about the three different pathways that provide energy for muscle contraction. So the first here seen all the way to the left is direct phosphorylation of ADP by creatinin phosphate. So the unique high energy molecule creatinin phosphate is found in muscle fibers, but not any other cell type. As ATP becomes depleted, interactions between the creatinin phosphate and ADP, adenosine diphosphate, results in transfers of high energy phosphate groups from that creatinous phosphate to the ADP, and then generates ATP within a fraction of a second. Although muscle fibers store perhaps 5 times much CP, creatinin phosphate, as ATP, the CP supplies are also soon exhausted in less than 15 seconds. Then we have the aerobic pathway, seen here at the center. At rest and during light to moderate exercise, some 95% of ATP used for muscle activity comes from this pathway, aerobic respiration. So aerobic respiration occurs in the mitochondria, involves a series of metabolic pathways that use oxygen. These pathways are collectively referred to as oxidative phosphorylation. During aerobic respiration, glucose is broken down completely to carbon dioxide and water, and some of the energy released as the bonds are broken is captured in the bonds of ATP molecules. Although aerobic respiration provides a rich ATP harvest, it is fairly slow and requires continuous delivery of oxygen and nutrient fuels to the muscle to keep it going. So it actually generates about 32 ATP for every molecule of glucose that is broken down. So it's quite efficient in the production of the ATP, but it does require that adage of oxygen, and consistent glucose. And then we have all the way in C to the right, the anaerobic pathway, or also known as anaerobic glycolysis and lactic acid formation. So the initial steps of glucose breakdown occur via this pathway, often referred to just simply as glycolysis, which doesn't need oxygen, which is why it's called anaerobic, without oxygen, without air. During glycolysis, which occurs in the cytosol, glucose is broken down to pyruvic acid, and small amounts of energy are captured in ATP bonds, about 2 ATP per 1 glucose. And as long as enough oxygen is present, the pyruvic acid then enters the oxygen-require aerobic pathway that occurs within the mitochondria to produce more ATP as described above. So it's kind of like a pre-step to the aerobic pathway, which is more efficient at producing more ATP, has a greater net gain of ATP. However, when muscle activity is intense or oxygen and glucose delivery is temporarily inadequate to meet the needs of working muscles, the sluggish aerobic pathways cannot keep up with the demands for ATP, and under these conditions, the pyruvic acid generated during glycolysis is converted to lactic acid, and the overall process is called anaerobic glycolysis. So let's talk about muscle fatigue. So when we exercise or use our muscles strenuously for a length of time, eventually those cells get tired, which leads to muscle fatigue. It just leads to this inability to contract even though it's being stimulated, or a vastly weakened contraction when stimulated. And there's a couple suspected causes. So just imbalance in ions and problems at the neuromuscular junction, and then oxygen deficit, which occurs during prolonged muscle activity. So there's just not enough oxygen to continue that aerobic ATP production. and then lactic acid begins to build up via the anaerobic pathway, and that's where you get that burning sensation from. So a lot of people will quote unquote train to failure, and this is what is happening, is they're just training to the point that oxygen is unable to participate in the aerobic ATP production, and that muscle contraction eventually gets flooded and, you know, with lactic acid and weakens and then stops. So this is why, especially for continual training throughout the week or progressive training, muscle recovery is pretty important, so that you're able to get optimal contraction when utilizing it. Here are the 5 golden rules of skeletal muscle activity. So 1, with a few exceptions, all skeletal muscles cross at least one point. 2, typically the bulk of skeletal muscle lies proximal to the joint crossed. So it's going to be, the bulk of that muscle is going to lie closer to the joint. 3, all skeletal muscles have at least 2 attachments, the origin and the insertion. 4, skeletal muscles can only pull, they never push. 5, during contraction, a skeletal muscle insertion moves towards the origin. Now let's talk about the types of muscle contraction. So we have isotonic versus isometric. So an isotonic literally means same tone or tension. Muscles will shorten. Myofilaments are successful in their sliding movements. Muscles shorten and movement occurs. So examples would be bending your knees, lifting weights, smiling. Isometric is when muscles do not shorten, they stay the same. However, myosin filaments are spinning their wheels and the tension in the muscle keeps increasing, trying to slide, but the muscle is pitted against some more or less immovable object. So the example in the book, which is a pretty good one, is when you push your hands together in front of you and your arms and chest muscles are contracting isometrically. So they're staying the same length, same measurement, but there is no movement really. They're not, you know, the action of lifting a weight, your muscle is going to contract and elongate. In an isometric movement, you're pushing against force. So there's no, the muscle is working, but it's not contracting. And then muscle tone is just the state of continuous partial contractions and the result of different motor units, which are scattered through the muscle, being stimulated by a nervous system in a systematic way. The effects of exercise on muscles. So we have aerobic versus resistant. So aerobic exercise is going to be your endurance exercising. So running, on the elliptical, HIIT. Stronger, more flexible muscles with greater resistance to fatigue. Blood supply to the muscles increases and the individual muscle fibers form more mitochondria and store more oxygen. It helps us to reach a steady rate of ATP production. It improves the efficiency of aerobic respiration, increases metabolism efficiency, improves digestion, enhances coordination, strengthens your skeleton, improves your cardiovascular health. However, you will not see the muscles increase in size for aerobic exercise. Resistance exercise is your isometric exercise for the most part. Pits the muscles against immovable or difficult to move objects. The key is forcing your muscles to contract with as much force as possible. So this, if anybody lifts, this is going to be what you're doing on your max lift days. Increased size and strength results, and it's mainly due to the enlargement of individual muscle fibers, and the amount of connective tissue that reinforces the muscle also has to increase. So there is merit to both, and pretty much the main takeaway, especially for you that all of you that are going into health professions, is that a body in motion stays in motion, that people should do what they're able to do, whether they're rehabilitating from an injury or they're trying to get into some kind of fitness routine. Body in motion stays in motion. People need to get up and move. Let's talk about some types of body movement. So there is about 600 skeletal muscles in the body, and all are attached to bone or other connective tissue structures at no fewer than 2 points. So we have the origin and the insertion at the very least. So the origin is attached to the immovable or less movable bone. So you can see in the picture, it's attached to the humerus, mid-bone. Hopefully mid-bone, you're not going to be having a lot of movement. And the insertion is attached to the movable bone. So that's why it's attached to the ulna in this case, and that the ulna is doing motion rather than the mid bone of, or the mid part of the humerus. Some muscles have interchangeable origins and insertions, and it's all depending on the action being performed. So, for example, the rectus femoris muscle of the anterior thigh crosses both the hip and the knee joints. Its most common action is to extend the knee, in which case the proximal pelvic attachment is its origin. However, when the knee bends by other muscles, the rectus femoris can flex the hip, and then its distal attachment on the leg is considered the origin. So some of these muscles, that's going to depend on what the body movement is, of whether it's the origin or the insertion. All right, let's talk about some of these body movements. So top left, we have flexion and extension. So flexion is a movement generally in the sagittal plane that decreases the angle of the joint and brings two bones closer together. So flexion is typical of hinge joints, bending the knee or elbow, but it is also common at ball and socket joints, for example, bending forward at the hip. The way I most easily remember this is when you're thinking about flex. You know, you're flexing to try to get your biceps, so you're closing that angle. And then extension is the opposite of flexion. So it's a movement that increases the angle or distance between two bones or parts of the body, straightening of the knee or elbow. So you think of flexing at the knee. You can see this young lady is putting her knee behind her. It's almost like flexing her arm, and then extending is putting that knee as far forward as it can go. And then you'll have things like hyperextension, hyperflexion at some joints. Then we have rotation. So rotation is movement of bone around a longitudinal axis. It's common movement in ball and socket joints, and describes the movement of the atlas around the dens of the axis. So shaking your head no. Abduction versus adduction. So abduction is moving a limb away, generally in the frontal plane, so moving your arm across your body away from it. And then adduction is moving a limb in the opposite of abduction, so the movement is toward the midline. So I always think of adding body mass to the center of the body. That's adduction versus abduction. Circumduction is a combination of flexion, extension, and abduction and adduction, commonly seen in ball and socket joints such as the shoulder. The proximal end of the limb is stationary, and the distal end moves in a circle. So you can see that, I'm trying to look to see where in the figure it is. So in D, so up in the second image at the top left, you can see the limb as a whole outlines a cone, as when you do like arm circles. There's some special movements. So we have dorsiflexion and plantar flexion. So dorsiflexion is pointing your toes up, and plantar flexion, planting your foot, is planting the toes down, which is how I remember that. It corresponds with the movement of the wrist as well. So moving your wrist as far back towards your the top of your forearm as possible is dorsiflexion, and moving it down, trying to touch the inside of your forearm, is plantar flexion. Then we have inversion and eversion, special movements of the foot. So inverting your foot, you're going to point that bottom of your foot towards the middle of your body, and eversion is going to be the other way, moving the sole of your foot to the lateral portion of your body. Supination and pronation refers to the movement of the radius around the ulna. So supination occurs when the forearm rotates laterally so that the palm faces anteriorly or up, as if you are trying to hold soup in your hand, how I remember that. And the radius and ulna are parallel as in anatomical position. So remember your anatomical position. Pronation is when the forearm rotates medially so that the palm is facing down, or posteriorly if you were standing up. Pronation brings the radius across the ulna so that the two bones form an X. So the book uses the same trick I just used, where supination is if you were able to hold soup in the palm of your hand. And the last one demonstrated here is opposition. So in the palm of the hand, the saddle joint between metacarpal 1 and the carpals allows an opposition of the thumb, opposable thumb. This is the action by which you move your thumb to touch the tips of your fingers on the same hand. It's a unique action that makes a human hand a fine tool for grasping and manipulating objects. Interactions of skeletal muscles in the body. So as we established in those 5 golden rules, muscles can't push, they can only pull us as they contract. So most often body movements result from 2 or more muscles acting together or against each other. Muscles are arranged so that whatever one muscle or group of muscles can do, other muscles can reverse. So in general, groups of muscles that produce opposite movements lie on opposite sides of the joint. Because of this arrangement, muscles are able to bring about an immense variety of movements. So in the figure we have in A, a muscle that crosses the anterior side of a joint produces flexion. And the example they're using here is the pectoralis major. So this is your chest muscle, or one of them rather. And then B is a muscle that crosses the posterior side of the joint, producing extension, would be your latissimus dorsi, your lat, which is part of one of your back muscles. So it's opposite muscles on opposite sides of the body causing opposite movements. C is a muscle that crosses the lateral side of a joint, producing abduction, so that movement away from the body. So the deltoid, the bulk of your shoulder muscle on the top of your arm, and the muscle that crosses on the medial side of the joint, producing adduction, is the teres major. So it's an antagonist to the deltoid. Here we have some definitions as well. So we have the prime mover, which is the muscle that has a major responsibility for causing a particular movement. Antagonists are muscles that oppose or reverse the movement. So we just went over a bunch of antagonists. Synergists are the ones that help the prime movers by producing the same movement or by reducing undesirable movements. And the fixators are specialized synergists. So they hold a bone still or stabilize it at the origin of the prime mover. There are several videos in your ebook about this, but so an example of a prime mover is and an antagonist is the biceps and brachii and the brachialis muscles of the arm, prime movers for elbow flexion, and they're antagonized by the triceps brachii, a prime mover of elbow extension. So again, the bicep and the triceps on opposite sides of your humerus, causing opposite movements. The synergists, an example of that is the flexor muscles of the fingers, cross both the wrists and the finger joints. You can make a fist without bending your wrist because synergistic muscles stabilize the wrist joints and allow the prime mover to act only on your finger joints, even though it does, that same muscle will cross the wrist. And then fixators, an example would be the postural muscles that stabilize the vertebral column. And they're also the muscles that anchor the scapula to the thorax. Sorry, my Siri was acting up. So there are seven different categories that we consider when it comes to the naming of skeletal muscles. So we have the direction of the muscle fiber. So imagine the muscles are named in reference to an imaginary line, usually the midline of the body or the axis of a bone. So rectus, meaning straight, an example of that would be the rectus femoris. And I think you can tell maybe from femoris that we're talking about the femur. An oblique, it runs at its slant. So a second thing to consider is the relative size of the muscle. So maximus versus minimus, maximus being largest, minimus being smallest, longest, long versus a short muscle in the same area. So the example is the gluteus maximus. The location of the muscle. So some are named for the bones with which they are associated. So an example here is the temporalis or frontalis muscles. If anybody's ever gotten Botox, you know that's where a lot of people get Botox, is and it overlies the temporal, and frontal bones of the skull. So the number of origins. So biceps, triceps, quadriceps. So biceps has 2 points of origin. Triceps have 3. Quadriceps has 4. The location of the muscle's origin and insertion. So occasionally it's named for the attachment sites. So the sternocleidomastoid muscle originates on the sternum and clavicle and inserts into the mastoid process of the temporal bone. So for some people, that'll be the triangle towards the side or back of your neck. The shape of the muscle. So some have a distinctive shape. So the deltoid is roughly a triangle. Deltoid literally means triangular, and you can think of the Greek letter delta, which is delta is signified by a triangle. And the action of the muscle, flexor, extensor, adductor. So for example, the adductor muscles of a thing all bring about its adduction. The extensor muscles of a thing, all, of the wrist in this example, extend the wrist. So now let's move on to the arrangement of fascicles. So skeletal muscles consist of fascicles, which we can see examples of in this figure, but fascicle arrangements vary, producing muscles with different structures and functional properties. So in a circular pattern as seen in A, the fascicles are arranged in concentric rings, so smaller to larger, and circular muscles are typically found surrounding external body openings, which they close by contracting, creating a valve. So the general term is a sphincter, aka squeezers. Examples would be the orbicularis muscles surrounding the eyes and the mouth. B, a convergent muscle. The fascicles converge towards a single insertion tendon, generally triangular or fan shaped, such as the pectoris major muscle of the anterior thorax, which you can see on the gentleman in the center as well, where it lies. It's your chest muscle. In a parallel arrangement seen in D, the length of the fascicles run parallel to the long axis of the muscle, as in the sartorius of the anterior thigh. And these muscles are strap-like. A modification of that is, you can see in C, is called fusiform. It results in a spindle-shaped muscle with an expanded belly, the bigger midsection, and tapered ends. An example would be the biceps. In a pinnate pattern, short fascicles attach obliquely to a central tendon, so at a slant. In an extensor digitorum muscle of the leg, the fascicles insert only one side into only one side of the tendon, and the muscles are unipinnate. If the fascicle inserts into opposite sides of the tendon, it is bipinnate. If the fascicles insert into several different sides, it's multipinnate. So you can kind of see the examples of those as well. So a unipinnate would be your extensor digitorum longus, a bipinnate would be your rectus femoris, and a multipinnate would be your deltoid. Now let's get into like the basic placement of your more superficial muscles in the body. You should be able to label these things on a diagram, so it's not a bad idea to make sure you're using your workbook, using empty images to label them. So first, let's look at the head and neck muscles. So they have two specific, there's special functions, and they fall into two large categories: facial muscles and chewing muscles. Facial muscles are unique because they insert into soft tissues such as other muscles or skin, and when they pull the skin of the face, they permit us to express ourselves by frowning, smiling, etc. The chewing muscles begin to break down the food for the body, so part of the first step of the GI system. All head and neck muscles we describe are paired except for the platysma, the orbicalis oris, the frontalis, and the occipitus. So the frontalis and the occipital, frontalis and occipitalis. Frontalis covers the frontal bone, runs from the cranial aponeurosis to the skin of the eyebrows where it inserts, allows you to raise your eyebrows, wrinkle your forehead, which is why a lot of people get Botox here so that you don't wrinkle in the front. And the posterior end is the smaller occipitalis muscle, which covers the posterior aspect of the skull and pulls the scalp posteriorly. The orbicalis oculi runs in circles around the eyes and allows you to close your eyes, squint, blink, and wink. And the orbicalis oris is a circular muscle around your lips, often called the kissing muscle. It closes your mouth, protrudes the lips. So this is how you do duck lips. The buccinator muscle runs horizontally across the cheek, inserts into the orbicalis oris, flattens the cheek, and as in whistling or blowing a trumpet. It's also listed as a chewing muscle because it compresses the cheek to hold food between the teeth during chewing. Zygomaticus extends from the corner of the mouth to the cheekbone. It is often referred to as the smiling muscle because it raises the corner of the mouth. The masseter runs from the zygomatic process of the temporal bone to the mandible. It covers the lower angle of the jaw, and the muscle elevates the mandible to close the jaw. So pretty important. And then the temporalis. It's a fan-shaped muscle overlying the temporal bone. It inserts into the mandible and acts as a synergist to the masseter in closing the jaw. Then we have the neck muscles. The platysma is a single sheet-like muscle that covers the anterolateral neck. So you can see here in this image, it's the bottom left larger muscle there. It originates from the connective tissue covering the chest muscles and inserts into the area around the mouth. Its action is to pull the corners of the mouth inferiorly, producing a downward sag of the mouth. The sternocleidomastoid, which we talked about earlier, is a two-headed muscle, and there's one found on each side of the neck. Of the two heads of each muscle, one arises from the sternum and the other arises from the clavicle, and the heads fuse before inserting into the mastoid process of the temporal bone. So if you can feel the bone behind your ear, that's your mastoid process, which you can see this is where this one inserts. If just one of these muscles contract, the face is rotated towards the shoulder on the opposite side and tilts the head, the head to its own side. Okay, now let's talk about some of the anterior trunk muscles. So we have the pectoralis major, so your pec. It's a large fan-shaped muscle covering the upper part of the chest. You can see here best in the left image. Its origin is from the sternum, shoulder girdle, and the first 6 ribs, and it inserts on the proximal end of the humerus. It forms the anterior wall of the axilla, so your armpit, and acts to adduct, would bring your arm to the center of towards the center of your body, and flex the arm. So, and then we have your intercostal muscles. So these are deep muscles found between the ribs. They aren't shown in the figure because the figure, the image here only shows the superficial muscles, but these are pretty deep. The external intercostals, which lie towards the lateral edge of the rib cage, are important in breathing because they help to raise the rib cage when you inhale. The internal intercostals, which lie deep and medial to the external intercostals, depress the rib cage, helping to move that air out of the lungs when you exhale forcibly. Now let's look at some of the posterior muscles of your trunk muscles. So we have the trapezius, often called the trap. So when people talk about their trap, they're usually just referring to the definition at the top of their shoulder, behind their neck, but you can see that the trap actually goes pretty far down here. So there's two of them, right? You have two sides of your body. The most superficial muscles of the posterior neck and upper trunk. When seen together, they form a diamond or a kite-shaped mass. So in this photo, in this image, you can just imagine the trap on the other side and it would make the shape of a diamond. The origin is very broad. Each muscle runs from the occipital bone to the skull bone, down the vertebral column to the end of the thoracic vertebra. So it goes pretty far down. They then flare laterally to insert on the scapular spine and clavicle. The trapezius muscle extend the head, so head extension. Thus, they are antagonist of the sternocleidomastoids. They can also elevate, depress, adduct, and stabilize the scapula. The latissimus dorsi, so often referred to as the lat. Two large flat muscles that cover the lower back. They originate on the lower spine and ilium and then sweep superiorly, so they sweep up to insert into the proximal head of the humerus. Each latissimus dorsi extends and adducts the humerus. They're very important muscles when the arm must be brought down in a power stroke. For example, if you're swimming or hitting something, hopefully not someone, just something. The erector spinae, or spine, the erector spine, is a group is the prime mover of back extension. The paired muscles are deep muscles in the back. Each erector spinae is a composite muscle consisting of three muscle columns, so the longissimus, the iliocostalis, and the spinalis. That collectively span the entire length of the vertebral column, so they extend the entire length of the back. You can see that in the right part of this image. They act as a powerful back extensor, but also provide resistance that helps control the action of bending over at the waist. So following injury to back structures, these muscles will often go into spasm and are also a common source of lower back pain. We have the quadratus lumborum. It's pretty fleshy. They form part of the posterior abdominal wall. Acting separately, each muscle of the pair flexes the spine laterally. So, if you're bending to one side or the other, but acting together, they extend the lumbar spine. They arise from the iliac crest and insert into the upper lumbar vertebrae. So this can also be seen in the right side of this image. So we could visualize the deltoid in the previous slide. However, this is just a better view and it demonstrates one of the places that you would give an intramuscular injection. So into the muscle, IM injection. So the deltoid is a fleshy triangle-shaped muscle, which we already discussed when we were talking about how muscles are classified, or named, so by shape. And it forms a rounded shape of your shoulders. Because they're bulky, it's a good site for injection. So, but usually for smaller amounts of medication, less than 5 ml. So most vaccines are 1 ml or less. The origin of each deltoid winds across the shoulder girdle from the spine of the scapula to the clavicle, and it inserts into the proximal humerus. They're the prime movers of arm abduction, so movement out away from the body. Now let's discuss some of the muscles of the upper limb. So these are the muscles that cause movement at the elbow joint. We have the biceps brachii. Most familiar muscle of the arm because it bulges when you flex your elbow. It originates by two heads, from the shoulder girdle and inserts into the radial tuberosity. This muscle is a powerful prime mover for flexion of the forearm and acts to supinate the forearms. Remember, palm up. The best way to remember its action is to think of opening a bottle of wine. The biceps supinate the forearm to turn the corkscrew and then flexes the elbow to pull the cork. Then we have the brachialis. The brachialis lies deep to the biceps brachii. Like the biceps, it is a prime mover in elbow flexion, and the brachialis lifts the ulna as the biceps lift the radius. So the attachment is just different. The brachioradialis is a fairly weak muscle that arises on the humerus and inserts into the distal forearm. Hence, it resides mainly in the forearm and aids elbow flexion. And then the triceps brachii. It's the only muscle fleshing out the posterior humerus. It has 3 heads, which is why it's called a tricep, that arise from the shoulder girdle and proximal humerus and inserts into the olecranon process of the ulna. Being a powerful prime mover of elbow extension, it is the antagonist of the biceps brachii and brachialis. Remember, the antagonist is just generally going to be on the opposite side of the bone and allowing the body to do the opposite action. So the biceps and the brachialis are able to flex at the elbow, and the triceps enables us to extend the elbow. The muscle straightens the arm, and the example in the book is in order to deliver a strong jab in boxing. Now let's move on to some of the muscles of the lower limbs, the lower extremities. So first we'll talk about the muscles that enable us to move at the hip joint. There's several you can see. The gluteus maximus, gluteus medius. So the gluteus maximus is a superficial muscle of the hip that forms most of the flesh of the buttock. It's a powerful hip extensor that acts to bring the thigh in a straight line with the pelvis. It's not very important for walking, but it's probably the most important muscle for extending the hip when power is needed. So when you're climbing the stairs or if you're jumping, it originates from the sacrum and the iliac bones and inserts on the gluteal tuberosity of the femur and into the large tendinous iliotibial tract. The gluteus medius runs from the ilium to the femur beneath the gluteus maximus for most of its length. The gluteus medius is a hip abductor and is important in steadying the pelvis during walking. So this one's pretty important for walking. It's also an important site for giving intramuscular injections, particularly when administering more than 5 mLs, which you can see demonstrated in the image on the left. Although it may appear that the large fleshy gluteus maximus, that forms the bulk of the buttock mass, the medial part of each buttock overlies the large sciatic nerve. So that's why we must be careful when we're injecting here, because we don't want to damage the nerve. The superiolateral, so high and to the side, quadrant that overlies the gluteus medius muscle, which is usually a very safe spot for the intramuscular injection. Generally, you do have to use a larger needle just because it is a deeper muscle. If anybody's ever gotten a penicillin shot in their butt, this is where they probably gave it. So the adductor muscles. So we already know what action they're doing, right? They're enabling us to bring that area of the body closer to the center of the body. The muscles of the adductor group form the muscle mass at the medial side of each thigh. As their name indicates, they adduct or press the thighs together. However, because gravity does most of the work for them, they tend to become flabby very easily. So special exercises are usually needed to keep them toned. The adductors have their origin on the pelvis and insert on the proximal aspect of the femur. So now let's talk about the muscles that cause movement at the ankle and the foot. Well, actually, this is at the knee, excuse me. So we have the hamstring group. Your hamstrings form the muscle mass at the back of your leg, the posterior thigh. consists of three muscles: the biceps femoris, semimembranosus, and semitendinosus, which originate on the ischial tuberosity and run down the thigh to insert on both sides of the proximal tibia. They are the prime movers of thigh extension and knee flexion. Their name comes from the fact that butchers use their tendons to hang hams, consisting of thigh and hip muscles, for smoking. I didn't realize that's where the name came from. That's kind of interesting. You can feel these tendons at the back of your knee. So go ahead and you can feel them behind your knee. The sartorius, compared with the thigh muscles, it's thin and strap-like, and it's not very important, but it is the most superficial muscle of the thigh, so it's hard to miss. It runs obliquely, so at an angle, across the thigh from the anterior iliac crest to the medial side of the tibia. So it runs from the outside of your hip towards the middle of your tibia, so towards the middle, down by your knee. It is a weak thigh flexor, and the sartorius is commonly referred to as the quote-unquote tailor's muscle because it acts as a synergist to help tailors sit with both legs crossed in front of them. The quadriceps group, so quad, we know it's made of 4 muscles, the rectus femoris and the 3 vastus muscles. They flesh out the front of your leg, your anterior thigh. Only 2 of them are visible, only 2 of the vastus muscles are visible, and the third is obscured by the rectus femoris muscle. The vastus muscles originate from the femur, and the rectus femoris originates on the pelvis, and all 4 muscles insert into the tibial tuberosity via the patellar ligament. The group as a whole acts as a powerful knee extender. So if any of you have ever played soccer, the kicking motion is done mostly by these muscles. Because the rectus femoris crosses 2 joints, the hip and the knee, it can also flex the hip. The vastus lateralis and rectus femoris are sometimes used as intramuscular injection sites. This is generally only in infants because they don't have those gluteal muscles yet. Okay, now we're going to talk about the muscles involved in the movement of the ankle and the foot. So first you have the tibialis, so you know it's attached to the tibia anterior. The tibialis anterior is a superficial muscle on the anterior of the leg. It arises from the proximal tibia and then parallels the anterior crest as it runs to the tarsal bones, where it inserts by a long tendon. It acts to dorsiflex, so point the toes to the nose, and invert the foot, so turn the sole of your foot towards the middle. The extensor digitorum longus, lateral to the tibialis anterior. The extensor digitorum longus muscle arises from the lateral tibial condyle and proximal 3/4 of the fibula and inserts into the phalanges of toes 2 to 5. It is the prime mover of toe extension, so spreading your toes. Fibularis muscles, there's 3 of them: the longus, the brevis, and the tertius. They're found in the lateral part of the leg. They arise from the fibula and insert into the metatarsal bones of the foot. The group as a whole plantar flexes and everts the foot, so points the toes down to the ground, plantar flexion, and everts, turning the sole of that foot towards the outside of your body, so which makes it an antagonist to the tibialis anterior. The gastrocnemius is a two-bellied muscle that forms the curved calf of the posterior leg. It arises by 2 heads, one from each side of the distal femur, and inserts through a large calcaneal Achilles tendon into the heel of the foot. It's the prime mover for plantar flexion of the foot, and for this reason is often called the toe dancer's muscle. If the calcaneal tendon is severely damaged or cut, so if your Achilles tendon becomes cut, walking is very difficult and the foot will drag because it's not able to push off the toe. So if somebody has an Achilles tendon rupture or tear, oftentimes you will see, depending on the size of their calf muscle, of their gastrocnemius, it will roll up like a window shutter. And then we have the soleus. So the soleus is deep to the gastrocnemius. It arises on the tibia and fibula rather than the femur, and it does not affect knee movement, but like the gastroc, it inserts into the calcaneal tendon and is a strong plantar flexor of the foot. So this image and the image on the following slide are going to show you the most superficial muscles of the anterior surface of the body and the posterior surface of the body. In your text in table 6.3, it'll have the muscles themselves listed, their origin, their insertion, and their primary actions. In your coloring book on pages 125 and 127, and it presents you with a similar figure where you go and label these things. And honestly, the best way to grasp where these things are is just to study. So I encourage you to use your coloring book against the image in the text and label that, and maybe consider making note cards to memorize, origins and insertions and what the primary actions of each of these muscles are. Let's conclude with some of the developmental aspects of the muscular system. So in a developing embryo, the muscular system is laid down in segments. And after those segments are laid down, they're invaded by nerves. Innervated, whatever you'd like to say. The muscles in their control by the nervous system develop pretty early in pregnancy, and the first movements happen around the 16th week of pregnancy, and this is called quickening. So this is when the mom can feel the fetus kick. After birth, baby's movements are gross reflex movements. Development of muscle control proceeds in a superior to inferior direction, which is why babies can reach for things before they can walk. Gross motor movement precedes fine motor, so before they'll be able to grasp things with their fingers, they'll be able to reach towards them. And it also proceeds in a proximal to distal direction. So they'll have more control towards the center of their body, and eventually that control will extend out distally. By mid-adolescence, we have reached peak level of development of this natural control. As we age, the amount of connective tissue and muscle increases and the amount of muscle tissue decreases, which is what makes muscles appear more sinewy as we age. And strength also decreases about 50% by age 80. Obviously, the rate of muscle depletion is different for everybody. Obviously, it depends on your workout regimen, your strength training regimen, your diet, but this is just in general, and probably within that same decade, everybody's going to have a certain percentage of loss. And here is your critical thinking question. While jogging, Mr. Amati was forced to jump out of the way of a speeding car. He heard a snapping sound that was immediately followed by pain in his right lower calf. A gap is visible between his swollen calf and his heel, and he is unable to plantar flex that foot. What happened? We'll discuss this in class. Any questions, comments, or concerns, please feel free to let me know.